Hi guys, welcome back to today's session. Previously, we were studying the inductive proximity sensor. Okay, in today's session, we are going to study about the photoelectric proximity sensor. These are also known as photo eye sensor, and we're going to see their working principle, their wiring, their application, and their construction. So let us begin. Just like any other proximity sensor, these are available in a wide variety of shape. They can be cylindrical, they can be flat. Now, in order to secure these onto a surface, they are equipped with these nuts or these holes through which a bolt can be tightened. If you look at the back end of the sensor, you will find that the connections can be internal inside the sensor body and only a wire is coming out, or there can be a connector of some sort. In this case, the sensor body and the wire are two separate things that needs to be joined together via this connector. Also on the body, you will find that there is a sensitivity adjuster which can be used to adjust or fine tune the range of the sensor. At the front end, you will find that these are the sensing faces of this photoelectric proximity sensor. Internally, these are equipped with two things. Number one is the transmitter, and number two is the receiver. Before we discuss anything, let us discuss that in some photoelectric sensor, there are two modes of operation. Number one is the light on mode, and number two is the dark on mode. By theory, the emitter will generate a beam of light, which will act as the signal light. Okay. Now, the receiver will receive this light. If it is interrupted by any target, then this acts as a actuation of the sensor. So in case of light on mode, if the light is shining on the receiver, if the light is shining on the receiver, then it will generate the electric signal. So this is like a normally closed switch. Okay. And if the dark on mode is present on the sensor, in this case, it will trigger a signal. It will give off a signal, electric signal, only if the light is interrupted by the dark or if there is no other light on the sensor. This is the dark on mode. So let us discuss the three to four different topologies of this photoelectric sensor. Number one is the through beam. Okay, in through beam, the transmitter and receiver are two separate units, and they are aligned together in a straight line at a certain distance. Now, this distance is the sensing range of the sensor. Okay, and it will be written on the operational manual of the sensor. The beam of light or the signal light will be emitted by the transmitter and it will be received by the receiver. If there is a target present, the signal light will be interrupted and this will trigger a actuation signal by the receiver. In case of retroreflective technology, because the through beam technology is a little bit expensive, it requires two separate units. So the emitter, the transmitter and receiver can be housed together into a single unit. So this single unit contains the emitter and the receiver. Okay, and at the opposite end there will be a reflector. It has a reflective surface and it will reflect the incoming signal light, okay, back towards the receiver. In case if the target cuts off this signal light, okay, the receiver will not receive this reflected backlight and it will generate an appropriate actuation signal. There is a problem with this topology as well. What if the target is reflective? What if it's a mirror? What if it has shiny surfaces? It can reflect back the emitted light back towards the receiver. In that case, the sensor will give a false signal of uh, object absence, and in case the target is present, indeed present in the path of the light. So, in order to overcome this scenario, there is an improved technology which is known as polarized reflective technology. What means that the sensor receiver has an additional circuit which acts as a polarized filter. What I'm trying to say that it can differentiate the beam of light reflected by the reflector and the beam of light reflected by the target based on the phase variation of the received light. So polarized reflective sensor, they get rid of this false signal which can be present in case of retroreflective sensor. The sensing range of the retroreflective sensor is less than the range of the through beam sensor because light has to bounce back from the reflector. In case of direct reflection, the target itself acts as a reflector. So emitter, it generates the signal light Signal light strikes the target, bounce back, and is received by the receiver. Okay, so depending on the color and material properties of the target, the gain has to be a much higher in this particular type of photoelectric proximity sensor, because the reflected back light signal can be of varying strength. If the target material is black and it has absorbent material, the light, the reflected light will be very less. So it has to be equipped with a very high gain of the receiver. Okay, so let us see how these are wired together. Now, in case if the emitter and receiver are two separate units, for example, in the case of through beam technology, the emitter just has to generate the beam of light. So it does not require anything extra. It just needs two wire. So in case of AC voltages, the brown wire will be connected to the phase and blue wire will be connected to the neutral. In case the emitter is operated with DC technology, the brown wire will be connected to the positive terminal of the battery and the blue wire will be connected to the negative terminal. So this is the complete wiring of emitter. Now in the case when the emitter and receiver are housed together in a single unit, this wiring is extra. All you need to focus on are the above four wiring topologies. Okay. Now, if we will combine the concept that we have discussed previously. For example, these sensor can be NO and NC, and some photoelectric proximity sensors are equipped with a selector, and you can select that whether the signal has to be NO or it has to be NC. One thing to keep in mind that brown and blue will always be the power wires. They will always be positive, negative, or phase or neutral. And the signal wire, if it is single, then it will be white or black. And if they are two signal wire, in the case of four wire sensor, they will also be white and black. They cannot be brown or blue because those are specific to the power wiring. So now if you look closely here, you will see that this sensor is selected towards anode terminal as indicated by this symbol here. So if the receiver does not receive any light, so this is the normal operation mode. So normally it is open and no signal will be coming from the white wire. However, when the sensor gets actuated, the normally open will now be forced close. The white wire will now conduct a electric signal generated by the sensor. In case of NC, the roles are reversed. In the normal operation, when there is absence of object, the white signal wire will continuously carrying the 24-volt signal. And when the object is detected, it will be forced open. The sensor will be actuated, and now there is no signal in the signal wire. In case of white and black, these are universal sensor. They can uh, they can generate an NC as well as NO signal. Under normal operation, you will receive the signal from white wire and no signal from black wire. In case of actuated signal, the role will be reversed. Now there is no signal from the white wire, but a signal from the black wire. Also, you will see that there is another selector, L and D. L for light on mode and D for dark on mode, as discussed previously. And we are missing one thing, that is the PNP and the NPN technologies within the sensor. PNP sensor will generate the positive signal from via its signal wires, and the NPN sensor will generate the negative signal from its signal wires. So you have to provide the signal respective of the technology of the sensor. So in case of PNP, the electrical load will be connected to the negative side, and in case of NPN, the electrical load will be connected towards the positive side, because the negative signal is provided by the sensor itself. So let us see some of the application of this photoelectric sensor. One is obvious. This is the for the counting of objects. So imagine that if you have a light on mode, so when the signal, sorry, if you have a dark on mode, when the signal is obstructed by this object, it will generate this pulse. Okay, and this pulse, according to the presence and absence of the object, this can be fed to a counter, and this assembly can be used for a counting application. So as we can see that this is using a retroreflective technology. So this is a photoelectric sensor with the emitter and the receiver, and the front side in a straight line there is a reflector which is bouncing back this beam. Here we see that these photoelectric sensors are used for triggering. So, for example, in the case of car wash system, as the uh, car interrupts this beam of light, the whole car washing assembly will start. So this acts as a starting signal. It can be starting signal to any motor, any conveyor, pump, etc. Also, in case when you are trying to trim or cut anything according to a standardized dimension, you have to provide a standardized reference on the sheet of material that you're trying to cut. Okay, so as the sensor detects this signal, it will provide the actuation signal to the cutter, and it will generate every time perfectly sized material. Okay, also these are used for signaling purposes. For example, these are roll of plastic film. Okay, these are used in packing machines, and over time these rolls are used up by the packets of the material being packed. Okay, so as it is running short, okay, the as you can see, initially the photoelectric sensor is receiving back the light signal. Okay, so this is the normal mode of operation. When the film is running out, okay, now the beam of light is not reflected back. It can be reflected anywhere else, or it can travel in a straight line, and this is now the actuation of the photoelectric sensor. It can generate an alarm or a signal on the HMI for operator, so that he can replace this plastic. The most common example is the checking presence and absence. For example, this photoelectric sensor is checking the presence of the lid on top of these bottles. Okay, whereas this sensor are detecting the bottle itself. So these are for checking and absence or presence of any material. In this scenario, you can see that this sensor, photoelectric sensor, specifically the retro reflective photoelectric sensor, is used to check the anomalies, and in this case, the jamming of the conveyor. Okay. Now, what we do is that we pair this sensor up with a timer, and if the sensor is actuated for a after a specific set of time, after a specific period of time, then this indicate that there is jamming on the conveyor, because the conveyor should be moving and there shouldn't be anything of that much time length. The object length is standardized and the pulse should be according to the length of the object. So if it is giving an signal for elevated period of time, then this indicates an anomaly or a jam. We can also use these through beam photoelectric sensor for controlling the height of the stack material. They can also be used for checking the limits of any machines. Okay, they can be used for fault detection. For example, in this case, we are seeing that whether the screws are properly seated into their holes. For example, this screw is okay, this is not okay, and this will trigger a signal or an actuator to push this screw down. Also, we can use this to control discards or scrap material. For example, now this is a scrap bottle. Okay, it is not properly filled and it is detected by the through beam photoelectric sensor, and we can this will signal an actuator that will discard this bottle. They can also be used for differentiating object, because we know that light is affected by the color and material properties of the object, and we can use this in order to differentiate between objects. Okay, they can be used for monitoring objects. For example, the caps coming out of this vibration motor, these are counted and checked by this photoelectric sensor, right? And they can be used to give verification signal. For example, in this lipstick assembly line, okay, this sensor will notify the actuator that the lipstick level is okay, and now the next step can be. So this that's all about it for the photoelectric sensor. I will see you in the next one, in which we are going to discuss the ultrasonic proximity sensor. So see you again. Bye bye.